This is Math 251, Section 11.5. In this section, we're going to begin to explore the reason why Calculus 3 is often called multivariable calculus. To look at that, we're going to explore this little table, and you're going to see this table several more times this semester. We're going to keep expanding on it. We're going to keep adding rows to it as we go along. Up until this point in your mathematical careers, the only type of function you've probably had to deal with is a real valued function of one variable, typically written in some kind of form like y equals f of x. As far as independent or input variables, there's just one, right? If it's written like this, the input variable is x, so typically x, but of course we can use any letter, and just one dependent or output variable, again typically y in a case like this, but could be any letter. We're now going to start to explore the idea that functions can exist that don't just have one input and one output. And the first type of function we're going to look at in this exploration is a vector valued function of one variable. Here's what they look like. Here's a two-dimensional one. R of t is equal to the vector x of t, y of t. Notice there's still just one input variable. T here is our input variable. But there's actually two output variables. The x component and the y component are both outputs, separate variables. So it might be 2, x and y, or it could even be 3 output variables. Here's the three-dimensional case with output variables x, y, and z. And again, as you can imagine, we could keep going. We could have a 4-dimensional or a 5-dimensional vector, so etc. here. I'll stop at 2 and 3 since those are the ones that we can visualize, but we could expand this into more variables if we wanted to. As far as handling vector-valued functions, the first thing I'm going to say is evaluating them you would probably do correctly even if you had absolutely no instruction, just based on your experience with functions. If I give you this two-dimensional r of t, this vector-valued function, and ask you to find r of 3, of course all I'm asking you to do is substitute 3 for the t. And so notice that our output is a vector, the vector 12, 28. So again, just to emphasize, we have one scalar input, and our output is a vector with 2 components. So one input, a 2-dimensional output. Here's another example. This one just is in the ij form, so r of t is cosine ti plus sine tj. And I'd like us to find r of pi thirds. So once again, I'm just going to plug in the pi thirds. And my result's going to be the cosine of pi thirds, which is 1/2 I plus the sine of pi thirds, square root 3 over 2 j. Again, one scalar input, a vector output with 2 components. So far, we're really just working in 2-space. We'll look at some 3-space examples a little later on. All right, the next thing I'd like to point out to you is that vector-valued functions are actually really closely related to something that you have already studied, specifically parametric equations. There's a very slight difference in how we interpret the output, But a lot of what you've already learned about parametric equations is going to help us out with vector-valued functions. Let's start with a standard function, y is equal to 4 minus x squared. And let's limit our domain to just -2 to 2. I'm going to start by writing parametric equations that represent that function. Remember that one of the easiest ways to write parametric equations, to represent a function that's given kind of in the standard xy form, is to just let x equal t. That means that y, I can get by just plugging in the t for the x, is simply 4 minus t squared. And since x is equal to t, that means our t values will go from -2 to 2. So there's parametric equations that say the same thing as this function does. If I now evaluate for t equal 1, so here's t equal 1. X, of course, is just t, so x would be 1. And y would be 4 minus 1 squared, or 3. And essentially, our interpretation for parametric equations is usually phrased in terms of time. We often interpret the t variable as time. So we might say, after 1 second, our object, whatever we're talking about, is located at the point 1, 3. Again, the difference between the parametric form and just the standard function form is that the t value is kind of part of the answer. We interpret it as a time rather than simply an x and a y. All right, let's do the same exact function now in our new vector-valued form. Once you have parametric form, it's very easy to write the vector-valued form because you already have the x and the y components determined. It's just a matter of writing those x and y components as a vector. So there's the x and the y written in vector form. Once again, I'm going to evaluate r of 1 in this case, so that's our t equal 1 in function form. And of course, I'll get 1, and 4 minus 1 squared is 3 again. As far as interpreting the results, I told you that there was just a very subtle difference in how we interpret the parametric situation versus the vector situation. Instead of thinking of the 1 second and a location, we'll think about the 1 second and a vector pointing to that location. So after 1 second, the vector points to the point 1, 3, as opposed to actually saying something is located at 1, 3. Again, it's a really subtle difference. When I draw the graphs in just a minute, you'll see what I mean. So let's compare the graphs of the original function, the parametric form, and then the vector-valued form. If I start with the original form, y equals 4 minus x squared for x between -2 and 2, that's just going to be an upside-down parabola shifted up 4. Plus and minus 2 are actually the x-intercepts. Makes y 0. So there's my graph. No big deal. What about the parametric form? The actual physical shape of the graph is no different because we are really representing the same function. The difference with parametric form is we now have direction. We are specifically going from t equal -2 to t equal to +2. So I know I'm going to show the direction on my graph as traveling from the original t value where x is -2 to the ending t value of +2. So with parametric equations, we get a directed graph. The shape is still the same as the original. It's just that we now have a direction of motion. All right, what about the vector-valued form? Once again, we're really talking about the same graph, so the basic shape doesn't change. But let's think about this interpretation again for a moment. The idea that at each time we have a vector pointing to the specific points on the graph. So for example, we had said at time 1, we get a vector that points to the point 1, 3. Like so. This is actually going to be true for every point on this graph. The output is going to be a vector that points out the entire graph. So in actual fact, and of course I can't draw them all, but I'll draw a sampling of them, the true graph of this vector-valued function is a set of infinitely many vectors whose tips are pointing out all of the points on that graph. Now, that's a pain to draw. And as a matter of fact, it makes the graph really messy and kind of hard to read. So typically, even when we have something expressed as a vector-valued function, we typically actually graph it as a parametric graph anyway, as a directed graph. And so we're going to kind of agree to do that as a convention. We'll plot only the points at the tips, just like we've done here, not the vectors themselves. And again, just keeps the graph uncluttered and more useful. But just know in the back of your mind, that is actually what the graph of a vector-valued function would look like. All right, just to practice, because I know it might have been a little while for some of us since we've done much work with parametric equations, let's do a few examples where I'm going to give you an XY form. We'll talk about changing to the parametric form. We'll do our new vector form, which is a short jump from the parametric, and sketch a graph. So I'm going to start with just a line, 2x plus 3y equals 6, from the point negative 3, 4 to the point 6, negative 2. If I would like to use my little trick of letting x equal t, I can do that. But notice that once x is equal to t, to get y, I'll have to do just a little bit of algebra. I would have 6 minus 2t divided by 3, or negative 2/3 t plus 6 divided by 3 would be 2. All right, what about the t values? Well, since x is equal to t, I'm just going to use the x values, which are going to be the same as the t values, and t is going to go from negative 3 to 6. So there's parametric form. To get vector form, I don't have to do too much. I simply rewrite this with the x component as t, and the y component is negative 2/3 t plus 2. Again, same limitations on the values of t. And of course, as far as the graph is concerned, we go from, it's just a straight line from negative 3, 4, our starting point, to 6, negative 2 is our ending point. It will be a directed graph in parametric or vector form, so I'll show the direction from starting point to ending point. All right, let's try another one. Y equals e to the x from 0, 1 to ln 5, 5. I'm going to use that same old trick again. x equals t. So y would be e to the t. And since the x value is the t value, once again I'll use the x's to define the range of values that I'm going to allow t to go through. In this case, 0 to ln 5. We'll turn that into a vector equation. T e to the t in vector valued form, with again the same limitations on t. As far as a graph, we all know what y equals e to the x looks like, just typical exponential growth. We're starting at 0, 1. Here. And we end at ln 5, 5. Let's see, what's the natural log of 5? It's about 1.6. So around here. We would end. And then I'm just going to show the usual type of a exponential type of curve, exponential growth curve in between there. Again, directed from the starting point to the ending point. All right, so a lot of times just letting x equal t is going to be the easiest way to parameterize your curves. The exception to this is circles and ellipses. With circles and ellipses, you can avoid a lot of unpleasantness with radicals and plus or minus signs if you parameterize using sines and cosines instead. So our last two examples are going to look at that. Here we have a circle, x squared plus y squared equals 9. We're going to go around once clockwise. And so to parameterize this, anytime you travel clockwise around a circle, you can always use x as the cosine term and y as the sine term. So I'm going to let x be cosine t and y is sine t. Now, this circle has a radius of 3. Right now, cosine t and sine t are on the unit circle, which would have a radius of 1. So in order to get that radius of 3 in there, I'll just put in my multipliers. X is 3 cosine t, y is 3 sine t. By the way, see if I can squeeze it in down here. Notice that this parameterization really does fulfill the original equation, right? If I were to plug these back in for x and y, x squared would be 9 cos squared t, and y squared would be 9 sine squared t. And if you factor out the 9 from the left-hand side, you use that trig identity, cos squared t plus sine squared t is 1. It's certainly true that 9 equals 9. So this is a correct parameterization. We want to go around one time. To go all the way around a circle, our angle or t values here would have to go from 0 to 2 pi. All right, we'll put that in vector valued form. 3 cosine t, comma 3 sine t, again with the t values going from 0 to 2 pi. And as far as a picture, it's just a circle of radius 3. And we are going around counterclockwise. Direction, of course, remember, is just the direction that we go around, just like the unit circle, even though this one has radius of 3. If x is the cosine and y is the sine, that does take us around counterclockwise. Circles aren't typically thought to have starting and ending points, but since we had a very specific range of t values, we can actually think of this as the starting and the ending point. Notice that if t is 0, 3 cosine 0 would be 3, and 3 sine 0 would be 0. So in fact, 3, 0 is like the starting point. And when I get all the way around to 2 pi, 3 cosine 2 pi is 3 again. And 3 sine 2 pi is 0 again. So we do get back to the same point that we started at. All right, one more. This last one is an ellipse, since it's got different multipliers here on the x and the y. And usually what I like to do here is figure out what the intercepts are, just to make my life a little easier. So the x-intercepts, if y is 0, I would just have 9x squared equals 225. See, 225 divided by 9 should be 25. And so x is plus or minus 5. And same idea for the y-intercepts. If x is 0, this just becomes 25y squared equals 225. So y squared is 9, and y is plus or minus 3. I'm actually going to reverse myself this time. I'm going to graph this one first, just to make it a little easier to talk about. The x-intercepts were plus or minus 5. And the y-intercepts are plus and minus 3. So the ellipse is going to look like that. All right, and there's one more thing we have to pay attention to before we start writing down our parametric form. Unlike this problem where we were going clockwise, x was cosine and y was sine, to get to go around the opposite direction, to get to go around, oh my goodness, I've just reversed that. I am so sorry. Because I've already drawn them, I'm going to reverse these. I drew this counterclockwise. I just read it wrong. Let's do me a favor and let's fix that. This one was counterclockwise. X is cosine and y is sine. This one, let's do clockwise. I wanted to show you one each way, and I just blew it. To go clockwise, this way, what we'll do is we'll reverse the sine and the cosine. That'll make us go around the other direction. So this time x is going to be the sine, and y is going to be the cosine. In the x direction, we want to stretch from plus to minus 5, so I'll put a multiplier of 5 there. And in the y direction, we want to stretch between plus and minus 3. So I'll put a 3 there. So one more time since I screwed that up. To go counterclockwise, x is the cosine and y is the sine. It's going to go counterclockwise. To go clockwise, x is the sine and y is the cosine. It's going to take me around clockwise. All right, we still only want to go around once, so we'll go ahead and let t go from 0 to 2 pi again. If I wanted to go around half a time, maybe I'd just go 0 to pi. If I wanted to go around 3 times, I could go from 0 to 6 pi. I can change that t value to affect how far I go around my circle or ellipse. All right, finally, writing the vector form. The vector equation is 5 sine t, comma 3 cosine t, again with t going from 0 to 2 pi. And notice that if I plug in 0 to start with, 5 sine 0 is 0, 3 cos 0 is 3. So I actually start at 0, 3 this time, as opposed to here where I started at 3, 0. We go around clockwise, and by the time we get to 2 pi, we're back to 5 sine 2 pi, which is 0, and 3 cosine 2 pi, which is 3. We're back to starting and ending in the same place again. All right, we will stop there and go on from there in the next video.